Can I get an amen out there? Can I get a fried rice too? There you go. God bless you. It's good to see everybody. Thanks for being here tonight. What a nice turnout. If you're not used to food truck etiquette, that's kind of how it goes. You get a line, you kind of go, but hopefully everybody got food and was able to enjoy. I'd like to say a big shout out to our Living Legacy group. Now, yeah, we can clap for Living Legacy. I'm okay with that. Our Living Legacy group has several things that they do, matching funds. Were just good works last Lent, thousands of dollars matched to Augusta Victoria Hospital in East Jerusalem, matched the water wells in Malawi, different events like that. They do scholarships, of course. Seminarian scholarship is brokered through them, and also the Biederman scholarships. And then providing for adult education and for our fall speaker series. And so we're so grateful for them. They have some literature out there at the table. So if you want to take a look, pick some things up, stuff about charitable giving and IRAs and all that kind of stuff. And I am pleased to let you know that this year for our stewardship campaign, our one-time giving option will be for Living Legacy. And so an opportunity to kind of bless that group for all their good work. So take a look at that. Thank you so much, Living Legacy folks that are here. You want to learn more. You came in, you go, I really want to give some money away today. So you want to talk to Barb. You'll take money for Living Legacy. You want to put your hand up in the air. Julie? Yeah, absolutely. Jerry Cochran is here somewhere. Where's Jerry at? Jerry will take your money. Bonnie's here. Bonnie will take your money. Anybody else from Living Legacy here? Dave wants your money, but don't give it to him. He's just going to take it to Vegas. It's going to be really bad for everybody, so don't do that. So folks from Living Legacy, it's just good to have people to talk to. If you want to know what they're about and who they are, take a look. It is my delight. This is our fourth annual Fall Speaker Series, and it's my absolute delight to welcome Dr. Grace Wolf-Chase here to Lutheran Church of the Resurrection. Dr. Chase's appointments are Senior Scientist, Planetary Science Institute, 2020 to present, also Senior Education Communications Specialist there as well, affiliated member of the Zygon Center for Religion and Science, astronomer for the Adler Planetarium Chicago, Associate University of Chicago Astronomy and Astrophysics, Senior Research Associate University of Chicago, Research Scientist, University of Chicago, Astronomy Lecturer, University of Nevada, Las Vegas, et cetera, et cetera. And since 2016, she has served as, you can't correct anything, you just got to say yes. She served as Vice President of the Center for Advanced Study in Religion and Science, which is an independent society of scholars and scientists from various fields who pursue critical interdisciplinary studies of possibilities for constructively relating religion and science. She has a heart for bringing science to faith communities. She has a passion for understanding in the best of the Lutheran tradition, you don't have to check your mind at the door when you come to worship here. That Lutherans were born in a university, and we embrace all the gifts that God has given us. And I just want to say, I don't know where else you'll get a tour of the universe in time and space in 40 minutes. Help me welcome Dr. Grace Wolf-Chase.
Thank you, Pastor. Thank you so much, Pastor Jeff, the Living Legacy Committee, for having me here, for establishing this great program. Carrie, Ramon, the wonderful people I've already met just in the few hours that I've been here. And not to correct Pastor Jeff, but I just want to explain that that whole list that he read, those are not all simultaneous. So I don't do all of those things at the same time. So tonight is going to be a really whirlwind tour of our amazing universe. We're going to look at a lot of what I'm talking about tonight in more detail during tomorrow morning's much longer presentation. So tonight is about sort of getting a glimpse of the big picture. Now, the idea of vocation as being called to serve God and neighbor in many different capacities is deeply ingrained in the Lutheran tradition. And for me, one of the ways I've tried to live out my vocation is to help other people get excited about science and to understand that science doesn't have to threaten their faith, but it can deepen and enrich it. And so I'd like to share a few of the personal experiences that have led me to where I am today, because I think it's important that you know something about the person who's talking to you. So I come from a very small, all-female family. I was born in New York City and raised in New Jersey by my mother and my maternal grandmother during the 1960s and 1970s. And informal education played a much larger role than formal education during my childhood years, which might be one of the reasons why I've worked for nonprofits for most of my career. My passions during childhood and adolescence were figure skating, astronomy, and science fiction, most notably the original Star Trek series on TV. Thank you. And science fiction was particularly effective because, one, at the time that I was growing up, most of the astronauts were male. Science fiction provided me with lots of different kinds of role models. But science fiction is particularly powerful because it's about telling stories. And stories, as we all know, are very powerful. Just think about the number of stories that Jesus told. So I was inspired to attend Cornell University by listening to Carl Sagan on The Tonight Show with Johnny Carson. Anybody remember Johnny Carson? Okay. With my mom when I was in high school. Now, sadly, my mom died when I was 19, and some very good friends helped me get back on my feet and get me back to school. So I graduated Cornell with a bachelor's degree in physics in 1981. I went on shortly thereafter to the University of Arizona, where I took a rather circuitous path through graduate school for many different reasons. But I got my PhD in astronomy in 1992. And my field of expertise is studying how stars and planets form. I've spent most of my career integrating scientific research with public education in many different ways, including something I'll tell you about at the very end, helping other people of all audiences participate in doing actual scientific research. So everyone has their influencers. These are a few of mine. Since graduate school, I've had several outstanding ones that have helped me relate science and religion in very profound and meaningful ways. So I first met the Jesuit astronomers of the Vatican Observatory when I started graduate school in the early 1980s. And after my family and I moved to the suburbs of Chicago in 1998, I was fortunate enough to establish many connections at what Pastor Jeff told you, the Zygon Center for Religion and Science, which is affiliated with the Lutheran School of Theology at Chicago. And I came to know some of the luminaries who were spearheading dialogue between scientists, theologians, and philosophers. Lutheran theologian Phil Hefner became a good friend over the years, and Antje Jacquelin was director of the Zygon Center when I started teaching astronomy to seminary students at the LSTC more than 20 years ago. I've also collaborated with Ted Peters, a Lutheran theologian who's associated with the Center for Theology and the Natural Sciences in Berkeley. We had a very nice discussion earlier, Pastor Jeff and I, about Ted, a mutual friend, and some of Ted's interests are putting the space sciences in conversations with theology and ethics, particularly regarding what we have learned in recent years about the likelihood of the existence of extraterrestrial life. So one more person I need to acknowledge here is Leah Schweitz, an amazing person, philosopher and theologian who had formerly served as professor at the LSTC in systematic theology, religion, and science, and is a former director of the Zygon Center for Religion and Science. She passed away just a couple of weeks ago from lung cancer. I remember Leah as a joyful, caring, and loving person, and one of the first theology professors to incorporate science modules into seminary classes. Soon after her diagnosis with stage 4 lung cancer 4 years ago, she started a Substack called Playdates with Death, which served as a forum to help people explore end-of-life issues with compassion and grace. So, this is a book, When Science Meets Religion, Enemies, Strangers, or Partners, that was written by Ian Barber about a quarter of a century ago. Ian Barber was another luminary in science and religion, and he outlined 4 categories for ways in which people view the relationship between science and religion, and I think it's useful to just mention them here. Enemies is probably obvious. This is the conflict thesis we've all heard about, where science and religion are considered to be irreconcilable. Strangers refers to they're completely independent. They have nothing to say to each other. There may be certain benefits for viewing them that way. However, I think particularly in the Abrahamic faith traditions, where we affirm that God is the ultimate source of the natural world, I think holding science and religion strictly separate is a little bit problematic. So I kind of fall where Ian Barber fell, that science and religion should work together as partners. And by partners, he meant 2 things. One, dialogue, that we should be able to talk to each other, share ideas, have discussions. But Barber also advocated a very cautious approach to kind of integrating, weaving together our scientific and religious views of the world into sort of a broader tapestry to increase our understanding of all of reality. So he was cautious about that, as am I. Our scientific and religious understandings are both very incomplete, so integrating them can be tough. But the things that I affirm are obviously taking science seriously, or I wouldn't have become a scientist in the first place. I advocate for 2-way conversations and a humble approach in all those conversations. And the Zygon Center has been about promoting these creative interactions between science and religion for decades. So I think Psalm 19 is a good place to start our actual tour. The heavens are telling the glory of God, and the firmament proclaims his handiwork. Day to day pours forth speech, and night to night declares knowledge. There is no speech, nor are there words. Their voice is not heard, yet their voice goes out through all the earth, and their words to the end of the world. So I think this is a wonderful lead-in to looking at how the heavens communicate knowledge to us through astronomy. So astronomy is by and large an observational rather than experimental science. And today we talk about multi-messenger astronomy, because we don't just collect the light that our eyes are sensitive to, visible light, but we collect all forms of light across the electromagnetic spectrum. My own research makes use primarily of invisible light, infrared light, microwaves, radio waves. This is the type of light we use to study the cold places where stars and planets first form. Many of the different wavelengths don't get through Earth's atmosphere, so we have to put some telescopes in space. We also get information from high-energy particles, bits of atoms like protons and electrons, that arrive from energetic events that occur in space. And gravitational waves were first predicted by Einstein's general theory of relativity in 1915 and only first observed 100 years later. And that's because we didn't have the technology until then to observe these tiny ripples in space-time. Yes, you heard me correctly. As science fiction-y as that sounds, that's what gravitational waves are, tiny ripples in space-time. So I think the cosmic calendar is a great tool for examining the big picture, the big cosmic picture as we understand it today. The history of our universe begins about 13.8 billion years ago, when the universe was in a very hot, very dense state, unfortunately known as the Big Bang. If you compress the 13.8 billion year history into one Earth year, on that scale, one cosmic second is about 500 years. This big history is accessible to us at our point in time because of the finite speed of light and because we live in an expanding universe with a finite beginning. The implications are profound. We have a fossil record of the past that comes to us from very distant objects in the universe and enables us to explore how the universe and its contents have changed over time. Now, you'll note on this cosmic calendar, our sun and the planets that orbit our sun, our solar system, don't even form until September of the cosmic year. And then the development of multicellular life doesn't occur till December on the cosmic year, with human civilization basically occurring in the last minute before midnight on December 31st. Modern science, as we practice it, is about one cosmic second old. Goes back about 500 years. Now, you'll note again that from September through December, this focuses on the development of life on Earth. However, as we'll see over the next couple of days, we also have some compelling reasons to think that these processes have occurred elsewhere in space, on other planets in the universe. So let's see how that time and space issue relate to each other. I don't know how many people in the audience here, like me, actually remember when this photo first appeared from the Apollo 8 capsule. The moon is about 250,000 miles from Earth. It takes light a little over a second to travel that distance. I do remember when we saw what our planet Earth looked like from the moon for the very first time. On the left here, you see a sculpture that commemorates Jim Lovell covering the Earth with his thumb, held at arm's length from lunar orbit because problems with the Apollo 13 capsule precluded the astronauts from actually landing on the moon. So I wanted to include these as a tribute. As some of you may know, Jim Lovell passed away in August at the age of 87. So let's go out to our solar system. Our solar system includes the sun and the various kinds of worlds that orbit the sun. Worlds we call planets, dwarf planets, their moons, asteroids, comets, and other small objects. Now, the planets closest to the sun are smallish rocky worlds like the Earth, and the planets further away are larger gaseous worlds like Jupiter and Saturn, and icy worlds like Uranus and Neptune, and the moons of a lot of the gas giants. Jupiter, Saturn, Uranus, and Neptune have a lot of small, rocky, icy moons. Now, on this scale, the speed of light becomes very important. The distance between the Earth and the sun is about 93 million miles, and it takes light 8 minutes to traverse that distance. So we could say that the sun is 8 light minutes away. And what this means is if there's a big flare on the sun this instant, we don't know about it for another 8 minutes. As we talk about communicating with spacecraft that are in the outer solar system, we're talking about communication times that span hours. And that's just in our solar system. So on this scale, those times become very important. Now, as we move out to other stars, these are some of the stars in the so-called solar neighborhood. Our sun is a star. Stars come in different colors, temperatures, sizes, masses, brightnesses. And this diagram just shows you a few of the different stars that are nearest the sun. Now, on average, stars are separated by a few light years. Not hours, not months, not days, but years, where 1 light year is about 6 trillion with a T, miles. So whereas the distance between the Earth and the sun is roughly 93 million miles, the distance between the sun and Proxima Centauri, the next nearest star, is about 24 trillion miles, which is over 250,000 times further away, and that's the nearest star to the sun. Now, for most of their lives, stars are powered by nuclear reactions deep within their cores that fuse hydrogen into heavier elements at the enormous temperatures and pressures at the cores of stars. About 70% of all stars are stars we call red dwarfs that are intrinsically about 100,000 times dimmer than our sun. And by intrinsically, I mean if you could line up the sun and a red dwarf at the same distance, the red dwarf would be at about 100,000 times dimmer. But they're very abundant stars. And they're kind of like the economy cars of the universe. They fuse hydrogen together on very, very lazy kind of timescales. The brightest stars at the other end of the spectrum, 100,000 times brighter than our sun, are very rare. They make up less than 1% of all the stars. None of those stars are in the solar neighborhood. But they're very important because those are the stars that explode as what we call supernovae after a mere few million years. They're the gas guzzlers of the universe, by the way. And they seed interstellar space with heavy elements that are essential to the development of life. So stars like our sun can go on fusing those elements for about 10 billion years. And these little economy cars, the red dwarfs, will be able to last trillions of years. And what that means that any red dwarf that's formed since the beginning of the universe is still in the prime of its life and will be for a long, long time. With the exception of the lightest elements, most of the natural elements on the periodic table were produced in stars, and the heaviest natural elements were produced in these supernova explosions where temperatures can reach trillions of degrees. It's also those explosions that distribute the elements produced during the star's lifetime. Without supernovae, a lot of those heavy elements would be locked inside of dead stars. Hydrogen and helium form in the early universe, and they're the most abundant elements in the universe. And it's something of a joke that astronomers, so chemists listen to this joke, astronomers refer to everything heavier than hydrogen and helium on the periodic table as a metal. I know, that's a big joke. Chemists would not consider everything heavier than helium to be a metal. So this graphic gives you an idea of the enormous range of size going from planets in our solar system to the largest known stars. Our sun is a little less than 1 million miles in diameter, and at the other end of the spectrum, we have this hefty guy, VY Canis Majoris, that's about 2,000 times as large as our sun. So those stars may look like little white, uninteresting points of light in the night sky, but they're really very different from each other. And I thought it was nice to include this little text from 1 Corinthians that speaks of the uniqueness of each star. Now, over the past few decades, using many different techniques, we'll talk a little more about that tomorrow, we've discovered more than 6,000 planets orbiting stars other than our sun. We call these planet-sized worlds exoplanets. And this graphic is an artist's representation. It's a wonderful representation that gives you a sense of the amazing variety of exoplanets. I know you can't read this. This actually should be a huge poster. So I'll tell you the important points here. All of these worlds are labeled with some kind of designation, not necessarily a name. Some of them just have a catalog entry. And they include all sorts of different sized worlds. Some of these worlds are similar to the gas giants like Jupiter and Saturn. Some of them are similar to Uranus and Neptune in our solar system. Some of them are similar to terrestrial planets like Earth, at least in size. We don't know what their composition is yet. But there are also many exotic worlds that don't have counterparts in our solar system, such as worlds we refer to as super-Earths or hot Jupiters. Hot Jupiters are huge worlds that orbit really close to their stars, and super-Earths may harbor large bodies of water on their surface. Now, this graphic includes 1,100 of the known exoplanets of all different types. And they're color-coded so that cooler planets look blue in this diagram, hotter planets look red. And so it compares their relative sizes in an artistic way and visualizes what they might look like. And I have to emphasize that, what they might look like. We don't have images, resolved images of any exoplanets at this point in time. We do, however, know that they're across the sky. So this is another graphic that just gives you a nice sense of how exoplanets, so it's a flattened representation of three-dimensional space, that these exoplanets orbit stars across the sky in different numbers per star. You won't see them, of course, because they're very faint and they're lost in the glare of their stars. It's only been in recent decades we've had the technology to detect them. So the sun, as well as all the stars you see in the sky and many more that you don't see, belong to an enormous group of stars that we call the Milky Way galaxy. We infer the overall shape of our galaxy by making measurements from our position in the galactic suburbs. Don't have a laser pointer, so I can't point it out, but our sun is not at the center of the galaxy, but about halfway out. It's okay, don't worry about it, I'm sure. Yeah, about halfway out. And so I am occasionally asked if I have a favorite star. And yes, I do. And it's Antares. And it's Antares because this woman, Nichelle Nichols, as Lieutenant Uhura, sang this beautiful song, Beyond Antares, that I remembered that I first heard when I was like 8 years old, and it's stuck with me ever since. And so that's why Antares is my favorite star. Now, the diameter of our galaxy is about 100,000 light years. And so what this means is it takes light 100,000 years to cross from one side of the galaxy to the other. So to look out into space is always to look back in time. We never capture the universe as it is now. And by the way, that also kind of applies to you guys. You guys in the back of the room, like Pastor Jeff, you're a little bit further in the past for me than Dennis is. But on this kind of a scale, it's a difference that makes no difference. But it does take light that long to cross our galaxy. Now, that dark lane you see in the plane of the Milky Way, that's not the absence of stars, but that's where we have these cold clouds of gas and dust that block the light from stars in the plane of our galaxy. And these are the places where stars initially form as gravity pulls them together. Now, we can't see them in visible light, but we can study them with infrared and radio telescopes. The fuzzy pink patches that you see there highlight where their stellar nurseries are first lit up by very bright stars that light up the gas, and you see the hot hydrogen gas around these stellar nurseries, and they show up as these little fuzzy pink patches. Now, you'll find the closest stellar nursery like that harbors some of those very bright stars in the familiar winter constellation of Orion. If I have amateur astronomers out there, you're probably familiar with the Orion Nebula. At a distance of about 1,400 light years, the Orion Nebula contains a large cluster of all sorts of different types of stars. And this is a Hubble Space Telescope image of the central part of the Orion Nebula from over 30 years ago. The dark foreground objects that you see in silhouette are roughly the size of our solar system, and they've been studied in great detail over the past 30 years. We have a lot of evidence that they are forming planetary systems. We also have evidence that our solar system formed in an environment much like this, in the company of luminous stars that exploded and enriched our solar system with heavy elements as it was forming. So the types of stars and planets that form in an environment like this depend on a wonderful array of complex interactions that play out over enormous scales in time and space. In recent years, astronomers like me have begun to use words adopted from biology like nature and nurture, which work very well as metaphors for how stars and planets actually develop. Now, the Hubble Space Telescope brought us many incredible views of the universe in visible light. The James Webb Space Telescope, or JWST, was launched 4 years ago to provide us with the deepest views of our universe in infrared light, and to address these four principal goals: to study the early universe, the first stars and galaxies, to study the formation of planetary systems, and to look for signs of molecules in the atmospheres of some of these exoplanets that might indicate those planets are habitable. Now, the JWST is like 7 times in light collecting area than the Hubble, provides higher sensitivity to faint light, as well as higher resolution. And the fact that it operates in the infrared allows us to probe further out into the universe and back in time. And that's a point we'll come back to tomorrow when there's more time. I'd like to show you a comparison of a beautiful image seen by both the Hubble Space Telescope and the JWST. Some of you may remember when this first came out with the Hubble Space Telescope 30 years ago, called the Pillars of Creation. And these pillars are a lot like buttes in the desert. So in buttes in the desert, you have these rock structures that are weathered down by wind and by rain. These pillars aren't made up of rock, but they're made up of gas and dust that's denser than their surroundings. And they're being eroded by harsh ultraviolet radiation off the upper right side of this image that's eating away into those pillars. And in the infrared, you can pick out different things that you can't pick out in the optical image, like the little red blips that you might be able to see from back there. I don't know, they're pretty small even from up here. But those are actually protostars, which are, if you will, prenatal stars or infant stars that are still in the process of growing. So these contrasting views give you some sense of how different telescopes complement each other and bring us different information. Another observatory that's expected to revolutionize our understanding of the universe, but in a different way from the JWST, is the Vera Rubin Observatory. The VRO is a ground-based optical telescope located in Chile that uses the world's largest camera, 3,200 megapixels, to survey the entire southern sky every few nights for 10 years. It's going to make the largest astronomical movie of all times, discovering new objects, tracking changes in dynamic processes in the universe. Among some of the changes and processes the VRO is going to track are the orbits of near-Earth asteroids that could pose potential threats to life on Earth. So this was one of the first light images released by the VRO. The Trifid and Lagoon nebulae are very similar to the Orion Nebula. However, these can be found in the summer constellation of Sagittarius, which would, of course, be winter in Chile in the southern hemisphere. This combines 678 separate images that were obtained by the VRO, and the pinkish regions are similar to those pinkish blips that I showed you in the Milky Way. They identify hot hydrogen gas in the midst of luminous, newborn, very, very hot stars, and the bluish regions are what we call reflection nebulae. It's reflection from dust that's near very, very hot, luminous blue stars. So regions like these, oh, by the way, the Lagoon Nebula, which is the one at the bottom end here, is actually visible to binoculars or a small telescope. So you can see that one with your binoculars. And stellar nurseries like this enable us to study how giant clouds collapse into stars, how star clusters take shape, and how young stars reshape their environments. So let's move even further out into space. On a clear, dark, moonless autumn night, you might be able to make out a smudge in the constellation of Andromeda. That smudge is the only galaxy beyond the Milky Way that you can see with your naked eye from the northern hemisphere, although you won't see it like that. It's the largest galaxy in what we call the local group, of which our Milky Way galaxy is also in the local group. And if you can spot that smudge, you might think about this. The Milky Way and the Andromeda galaxy are approaching each other because of their mutual gravity. No fear, they won't merge for another several billion years or so. They're expected to merge into a really huge galaxy, and when galaxies merge, individual stars don't collide because stars are small compared to the enormous distances between them. So this is our nearest spiral galaxy neighbor. The light from Andromeda that we see today left Andromeda 2.5 million years ago, before anatomically modern humans existed on Earth. As we go out further, we see an enormous variety in the shapes of galaxies, and these shapes tell us a lot about galaxies' history. For example, these antenna galaxies down here are an example of merging galaxies. So even though on really large scales the universe is expanding, in galaxy clusters, gravity dominates, and galaxies can actually come together and merge. And even though the individual stars don't collide, cold interstellar clouds get compressed, and that results in a lot of star formation. So those fuzzy pink patches in the antenna galaxies, in the whirlpool galaxy, are extragalactic examples of stellar nurseries like Orion, Trifid, and Lagoon in our galaxy. So this is another nice example of what happens when you put together light from different telescopes. This is a combination of Hubble and JWST views of two galaxies. So here we're using colors that our eyes can interpret to represent both visible and invisible infrared light. And what I love about this is also a pair of galaxies that grazed each other about 1 million years ago. And you can see in those reddish rings, you can see these very, very bright blue-white stars, or maybe you can see them from the back of the room. I don't know. It's very difficult to pick them out. But basically, you can see all these pockets of star formation that take place as gas becomes compressed and forms new stars. So this image you're going to be seeing a lot of over the next few days because jaws should be dropping now, right? Okay. Here's another one of the amazing first images released by the Vera Rubin Observatory. You're looking at a part of the Virgo cluster where you would need, thank you, where you'd need 400 ultra-high definition TV screens to display the entire image, which is about 45 times the area of the full moon on the sky. And you can see prominent spiral galaxies, merging galaxies, galaxy groups near and far, stars within our own Milky Way, and much more. And this was obtained with really not a whole lot of observing time. This is one of the very first light images that the VRO took. Going out to a larger view of the Virgo cluster that was made up from over 1,100 individual images. In this image includes about 10 million galaxies, which is a small fraction of the approximately 20 billion galaxies the VRO is expected to capture over the next decade. The incredible views we get of galaxies from observatories typically come from boring patches of sky to the unaided eye. I don't know if you're very familiar with the constellation Virgo, but it's not all that exciting. And yet, so we need to look away from the Milky Way in our own galaxy. Milky Way contains the highest concentration of stars, gas, and dust. So we need to look away from the plane of our galaxy to capture some of these incredible images of galaxies. So here the VRO transforms seemingly empty pockets of space into these glittering tapestries. And the Virgo cluster is still relatively near the Milky Way as far as cosmological distances go. So I'm going to step through a few of these relatively quickly. Over the years, the Hubble Space Telescope took several deep views into our universe by collecting light over the course of days or weeks from seemingly empty patches of sky. And in this entire image, you don't see all of it here, There are nearly 10,000 galaxies. The image itself is only about 1/10 the diameter of a full moon. And the brightest and most defined galaxies are at a distance of about 1 billion light years, and the smallest and reddest are at a distance of about 13 billion light years, so coming to us from a time when the universe was very young. We can step out to even larger Hubble fields, like the size of the full moon on the sky, and in the Hubble Legacy Field, you can find roughly 265,000 galaxies. The light from some of these comes to us from a time when the universe was about 500 or so, or less than 500 million years old, which sounds like it's really old, but on the timescale of the entire universe, it's not all that old. So in this picture from the JWST, that little red blip, you're looking at what I think is the most distant galaxy thus far identified, whose light comes to us from a time about 330 million years after the Big Bang. And an international team of astronomers recently identified powerful hydrogen emission from this galaxy at an unexpectedly early period in the universe's history. So the neat thing about capturing light from these very distant galaxies is they promise to tell us a lot what was going on when our universe was very young. So I don't know about the rest of you, but I love numbers. So let's have some fun with numbers for a few slides. There are roughly 200 billion stars in the Milky Way. In the part of the universe that we can actually observe, we don't really know how large the universe is, but there are more than 1 trillion galaxies. If you multiply number of galaxies by the number of stars per galaxy, you come out with a number with 23 zeros. Now, by comparison, there are an estimated 10 million quadrillion grains of sand on all the combined beaches on Earth. And that's a factor of 10 smaller. One way to think about this is there are roughly 10 stars for every grain of sand on every beach on Earth. For every star, we estimate an average of 1 to 3 large planets. For every star, on average, there are 1 to 2 habitable locations somewhere in the system, either on planets or moons of planets. In our galaxy alone, we estimate that there are more than 20 planets for every person who has ever lived. The estimated number of at least potentially habitable worlds in our universe is a number roughly with 24 zeros. So more fun with numbers, and this is just, again, to have fun. Each neuron in the human brain is connected to about 10,000 others via 1 quadrillion synapses. It's roughly the number of stars in what we call a supercluster of galaxies. If you multiply that number by 8 billion people on Earth, you come up with a number that's in the ballpark of the number of estimated habitable worlds in the observable universe. And I don't mean to imply that there's any kind of a connection there. I just think this is really cool. Huh? Cool? Yeah. Now, but wait, there's more. The paradox of not knowing is that the paradox of knowing is that it creates more not knowing. The more we know, the more we realize how much more we don't know, and that should keep us humble. In this brief tour, we've been talking about what we call normal matter, labeled as atoms on this pie chart. Less than 5% of the universe is estimated to be made up of this stuff. We'll talk more about dark matter and dark energy tomorrow. For now, I'll just say that both have been important in shaping the evolution of the universe. So to give you a taste of some of the things I'd like to talk about tomorrow, the universe is rational and understandable to us, at least in part. We'll talk a little bit about what that means. The universe has only gotten bigger as we learn more, hasn't gone the other way. If we discover life relatively nearby, that would imply that the universe must be teeming with life. However, not discovering it doesn't mean it's not there. The universe is just too big. We can never say with certainty we are alone in the universe. The universe displays an intricate network of relationships of which we are a part, not apart from. How do these observations affect the way we think about God? We'll talk a little bit more about that tomorrow. I do want to note this quote by theologian Michael Yaconelli, who says, "We have lost our astonishment. The church should be full of Christians who seek questions rather than answers, mystery instead of solutions, wonder instead of explanations." And I want to put up one more slide because I want to end by letting you know about some platforms where everyone can contribute to actual research projects. CosmoQuest is an initiative spearheaded by a colleague of mine at the Planetary Science Institute. And one of the things you can do on this site is help scientists map other worlds in our solar system. Zooniverse is the world's largest platform for what we call people-powered science. It harbors projects in the sciences and humanities that everyone can contribute to research in subject areas that interest them. And sometimes they even make significant discoveries, and you can communicate with the project researchers in many different areas. People have discovered new planets, new types of galaxies, in my field, even prenatal star clusters. Periscope is a research activity designed by my colleagues and me, primarily for students in introductory astronomy classes. I've included the QR code for anyone who's interested in learning more. This would be primarily for people who maybe teach astronomy at a high school or early college level. You can sign up through that site to join a mailing list we'll use when we start recruiting teachers, which will probably be several months down the road. You're also welcome to contact me by that email anytime with questions about some of this stuff, about this participatory science or citizen science, as it's sometimes called. Science, like faith, is a journey. It's a process. And like faith, it involves community, communication, and collaboration. Everyone can participate. Thank you all so very much. And one more thing I just want to mention, I do have some brochures about Zooniverse or some flyers with the website on the table down there too, so please feel free to take whatever you want.
One more hand, Dr. Grace. Dr. Grace, thank you. So I don't know about anybody else, but what I'm taking away is a whole new appreciation when people say we are not alone. And I don't mean that necessarily by intelligent beings, but we are not alone in the immensity of what we would call creation. And in the incredible imagination of a God who is creator and continues to create. And I think that's just an amazing thing as we kind of begin to think about. I think it's easy on our little, it's easy on our little patch of earth in Lynn County, Iowa, to only think about Lynn County, Iowa, or the United States, or et cetera, et cetera. And the reality that we are a part of such an interesting and marvelous and beautiful creation, I think should give all of us just a real sense of awe and wonder. So that's just a wonderful thing. We have time for just a couple questions. We're going to make sure that we're done by 8 o'clock. And so just a couple of questions. But I also want to remind you, if you have some questions, tomorrow we'll have extended time for some questions. And but if there's anything that you just want a quick clarification on tonight, just shout it out. And otherwise, we will move on with our evening. So is there anybody has something that's just kind of burning, or you missed something that you just want to get clarification on?
Or even if you just want to make a comment. Yes, sir, back there.
You had said that everything
Not everything we observe is round, but planets and stars are round because of gravity, because of the way gravity works and pulls them together and shapes them as being round. In fact, it's interesting. There are a few shapes we see repeated quite often in astronomy, and there are actually good reasons for that. The round shape, because of the way gravity works, but also there are these powerful jets that I don't think I'm going to get a chance to talk about at all, that we see on many different scales. When planets are forming, from black holes, from a lot of exotic things in the universe. So there are some patterns, and in the shapes of galaxies too, there are shapes that repeat depending upon the galaxy's history, how fast it's spinning, how fast it's rotating. So yes, so there are shapes that we see that basically come out of the physics, of the wonderful physics involved. But yeah, no, not everything is round. Just big things tend to be round.
Yeah, thank you. Any other little clarification question or? Yeah, just go ahead and yell it out real loud so we can all hear it.
So you were going on with a number of possible habitable planets that could exist. When looking at that, are you looking at the temperature, water, the things that we know of as life in the broad sense? Because what humans need for life is not the same as everything that lives on this planet.
Absolutely, but there is one.
Before you go, just so for folks, because we're recording, so the question was, when you talk about habitable planets, what's the criteria? Is it just kind of what we know, or is it broader?
Yes, so that's a very good question. And there is one thing that all forms of life on our planet need, and it's not oxygen, it's water. And so NASA tends to be following the water, but by the same token acknowledging, by following the water, I mean looking specifically at worlds that are likely to have water. And there are other planets even in our solar system that are known to have subsurface water, so we haven't ruled out the fact that there might be life, for example, under the icy shell of Europa and in other places in our solar system. But it's easier to look for what we know to start there. But there, believe it or not, there's a branch of the NASA Astrobiology Institute, I'll mention astrobiology more tomorrow, that's investigating so-called agnostic biosignatures. And what they mean by that is looking for life that could be based on different chemistries and might not need the things that we need, but might be a different kind of life. So yeah, there are people certainly thinking about that. And being a science fiction fan, I always used to love the aliens that were least like us. I don't know if we have any other Trekkers among the audience here, but my favorite episode was called The Devil in the Dark, and it was about a silicon-based life form that basically looked like a large pan pizza. And it was mostly rock. And I loved that because it was one time we got an alien that didn't look like a blue human or a human with pointy ears or something like that. I love thinking about those things, yeah. Good question.
They've got one more, and then the rest will have to come back for tomorrow.
Please do.
Well, Dan had the hand in the back, so I wanted to go there first.
I think I've heard that the universe is continually growing.
So the question was, is the universe continually growing?
The universe is expanding, or what I should say is space-time is expanding, and that's something we'll talk a little bit about more tomorrow. So it's not like galaxies themselves are growing, but the space between galaxies expands in time. And that was actually another prediction that came out of general relativity and Einstein early. It's incredible. General relativity made this whole long list of predictions, so many of which, were actually verified. And then there was this thing with the gravitational waves that Einstein noted that this was a prediction of general relativity, but he said, yeah, we'll never be able to detect those. Well, we did. It just took 100 years in order to do that. But yeah, it's space itself, or really space-time. Again, more about that tomorrow. Always a hook for tomorrow, yeah.
Okay, well, my guess is you may have a few minutes as people leave, perhaps tonight.
Yeah, I was going to pack things up, so
Yep,
yeah.
so we'll give you 2 or 3 minutes, and then we have to get Dr. Grace on her way. But in the spirit of Star Trek, but Next Generation, to all of you mostly ugly bags of water. Do you know that one?
Yes, I do.
Yes, you do. So for all of you that came out tonight, God bless you. I hope you get a chance to come back tomorrow. Certainly to look at the Living Legacy table. Also then on Sunday, we have just a full week. And what an amazing universe we live in. And what an amazing God we have that brought it all together. So for all your work and for all scientists who study and help us learn more, we are so grateful. And how about one final round of applause for Dr. Grace Wolfchick.
Thank you, Pastor Jeff. And I definitely don't want to dissuade people from coming back tomorrow, but if it turns out you absolutely can't, you can contact me by email. I mean it. If you have further questions or you want to explore citizen science and you've gone to the Zooniverse site or some other site and you want to understand more about how all that works, please, by all means.
Great, thank you. Have a good night. God
Thank
bless
you.